parameters of the random variables that we are adding up to make this V, right? So this is just a nice technique, and this is essentially how you have to derive through these concepts. And basically, if you are asked to derive any function for, let's say, V in this case, or in any another case in general, you will have to do such method. And see, it's easier to write the formula, substitute in until you get here, because this is where you have to really use your table booklet and see and do all the trial and error. So the very first thing that helps you is to check what is unique about this thing which is inside the summation. So we saw that we have m factorial and then we have v minus m factorial. So we knew that if I can add v factorial in the numerator here, it could look a bit like binomial distribution if I just adjust this and take this again inside, right? And then ideally we did get our answer, which was also with mu plus lambda as the parameter for our random variable v. So again, we started off with thinking as if it could be a negative binomial, but then we discarded it immediately because in negative binomial, we had k plus x sort of something, right? And here we just don't have that. So in the numerator at least. So that is how you have to go about solving these questions. And it does require a bit of a time and a bit of a practice to get adjusted to solving such questions. But the more you practice it and the more you do not look at the answer prior to solving it, you will be habituated to the way of finding patterns and finding commonalities and thus coming up with the answer as fast as you would like to in an exam. All right, so that is just a question. Oh yeah, sure.
Can you please explain the last step, how you went from VCM to the last step where you wrote in the bracket lambda plus mu raised to V?
This? Okay, so if you open your table booklets on page number 6, you can see the binomial distributions PDF, right? What is it? It says it is n x p raised to x and q raised to n minus x. So again, for us to check whether this actually follows binomial distribution or not, the very first thing that we should check is that the thing that we have here is the same that we have here. We do, right? N, we have v, and this n should be the addition of this and this as well. So we have m and v minus m. So it adds up to v, like you have it there, and you have m here. So this is the n that you have, and m is the x, right? Because we are summing up over x till v. So this is m behaves as s, x, and v is behaving as the n here. And this is just the way to expand this. So if you have a look at this PGF as well, you can see that it is, q plus ps raised to n. So over here, our s is just 1. And okay, let me maybe write how we define the PGF. Does anyone know how I define a PGF? What is a PGF? Anyone? Has anyone heard of PGF before? So the way you define, it's just another form. You have MGF, PGF, and CGF, right? So the PGF is defined, let's say it should be like, expectation of t raised to x. So here x is the random variable that you take into consideration. And it will just be e raised to e expectation of t raised to x. Does this make some sense?
Yes, ma'am. Thank you.
All right. What about others? Any doubt?
Ma'am, I still didn't understood that last part. Can you please explain once again?
You still didn't understand? Okay, so maybe instead of looking at the PGF, what we can do is we can also have a look. So if you go to page number 2 in your table booklets, you see a binomial expansion, right, of a plus b to the power n,
Yes, ma'am.
right? So if you start off with m taking the value 0, you are essentially getting this whole series, right? Because if your m is 0, what will you have first? V0, which will just be 1, right? Because the way of choosing 0 numbers is just 1. So you will have an m is 0, so this would also be 1. And you will only have lambda raised to v, right? Which will be acting as your a raised to n here. So if you just look at that binomial expansion, and if you compare this thing, this is exactly this. So your A is lambda, your B is mu, and your N is V.
Okay, got it. Thank you.
Anyone has any more doubts? So let me maybe just, write it somewhere here. All right, so clear now?
Yes, ma'am.
Any more doubts?
No.
No? Okay, so I will start sharing my screen. Yeah. So we did up until MGF and we just now saw how to solve a sum if you have, addition of two Poisson distributions. So let us now try to see what happens if we have to derive sum of, so let's say, again, whenever I'm talking about defining a compound distribution, we know that, whenever we have a compound distribution, we have two distributions actually in place. One is the distribution of the n, which will be discrete, of course. And the other thing is the distribution of x, right, which will be continuous. So again, for now, what we can do is we can maybe ignore the distribution of x and just work with knowing the distribution of n, because that is what at the end defines the name that will be assigned to the compound distribution that we are having a look at. So let's say I define my S as I do always, xi, and this is a compound distribution. So what will happen now is, if I give you guys some more bit of information, so let's say if I tell you that my n now follows Poisson distribution with the parameter lambda, then my S will follow a compound Poisson distribution. So remember, whatever will be the distribution for n guy here will be the thing that you will have here for the S. Okay. So now if I am telling you guys that, my S follows a compound Poisson distribution, let us try to analyze its characteristics, which would be expectation, variance, MGF, or even skewness. So, okay, here I will be talking a bit about skewness as well. So again, even before we derive the skewness, what do you guys think the skewness of S would be? Will it be positive, will it be negative, or will it be zero? So will this distribution be positively skewed, negatively skewed, or symmetrical? What do you guys think it should be?
Maybe positive because poison is positive.
Yeah, so this poisson is positive, all right. Yeah, that is one of the reasons, all right. Any other reasons? What about others? What do you guys think? Do you all agree with what she just said? Okay, so let us derive through it and then we'll check what happens at the end, okay? So the very first thing that we know is that n follows Poisson with parameter lambda, right? So if I were to write my expectation of n, what will that be? Anyone?
Lambda.
Lambda. My variance?
Same lambda.
Same lambda, right? Because for Poisson it is just the same. And my MGF would be e raised to lambda times e raised to t minus 1. So again, this I have just taken from the formula booklet. All right. So now I have to derive some things about my S guy here. All right. So let us try to write expectation of S. So we do not remember the formula. So we'll go and have a look here. So what is my expectation of S? It is just expectation of X times the expectation of N, right? So remember, again, we're defining only N here. So I'll just first will write this as expectation of N times the expectation of X, and I'll write expectation of N as lambda as it is. And for this guy, I'll just use M1, M2, and so on notations. So basically, I'm saying that for my X, if I have to define expectation of X raised to K, I'm going to write it using this notation. All right. So my expectation of X raised to 1 will just be M1. All right. So now if I have to figure out my variance of S, again, we go back and we have a look at the formula. Can someone dictate to me the formula for variance of S here? What was the thing that we highlighted in the previous lecture?
M2 minus M1 the whole square into expected value of N plus M1 square into variance of N.
Right. So this will remain as it is, right? M2 minus M1 square. And what is my expectation of N? Lambda plus M1 square, variance of N, again lambda. So what will happen? M1 square lambda, M1 square lambda. This is minus, this is plus. Cancel. And you'll be only left with M2 times lambda, right? So you have lambda times M2. That's it, right? Okay. Now let us try to figure out Ms of t. What was the formula for this? It was something like Mn, and then instead of t, you had log of mxt, right? So what do you think I should be doing? Instead of t here, I have to substitute this guy, right? Okay, let us go step by step. So first I'll just write e raised to lambda, e raised to log of mxt minus 1. What do you guys think should happen next? What will come in within the brackets? Anyone?
MX2 minus 1.
Exactly right. E and log will cancel each Yeah, sorry about some internet connectivity issues, but I guess you guys can hear me now. Can you guys?
Yes, ma'am.
Yes.
All right. All right. So what was I saying? Yeah, I mean, in Poisson, it's a bit easier because we have expectation in lambda, variance as lambda, and that's it. So now let us try to see how do we derive skewness. So do you guys remember how to derive skewness? Do you guys remember that monstrous formula that we have to use to derive skewness? Does anyone remember that? I don't. So let us try to, maybe not use that and see if we can maybe use something else to derive the skewness. So what is the other thing that I can use to derive the skewness? Do you guys remember CGF, cumulative generation function? So what happens is C prime of X at 0, C double prime of X at 0, C triple prime of X at 0. Does anyone know what values this will give me?
All will be lambda.
All will be lambda. Why do you think so?
No, I guess that will be for MGF, not for CGF.
Okay, but again, I have written X here, right? I haven't written S or I haven't written N here. So I really don't know anything about my X here as of now, right?
It will give central movements.
It will give us central moments. So this, if you differentiate once, it will give you expectation of X. If you differentiate it twice, it will give you variance of X. If you differentiate thrice, it will give you skewness of X. Okay, that's done. But how do we define a CGF? How do we define a CGF?
Log
So
of
if I were
MGF.
Log
to,
of
Log
MGF.
MX.
exactly, right? So it is just the log of my MGF. All right. So now, first of all, let us try to derive the CGF for our S, right? Because that is what we want. We want the skewness of our S, right? So we'll try to derive it. Let's see. So we want CS of T, and that will be, as you guys said, log of MST. And I think we just derived the MST. So let me just rewrite it. And it was something like e raised to lambda, and then e and log got cancelled out, and we were left with mx of t minus 1. And this is all within the brackets for our log cut. So what do you think will happen again? This log and this anti-log will cancel each other out, and you will only be left with what's there in the power. So we have lambda times mx of t minus 1. But again, now we are stuck, right? Do we really know anything about our mxt? Can we simplify it further? No, right? So let us try to see what happens if we differentiate it. So because to derive the skewness, I have to differentiate it thrice, right? So let me just differentiate it once. If I differentiate it once, what will I get? I'll have d upon d. What should I write here? What should I be differentiating this with respect to? Anyone?
T.
T, right? So this will just be T here. All right. So what will I get next? Can I simplify this thing further?
It will just be lambda into mx dash of t.
Right. So it will just be lambda times mxt prime. So this is, I mean, again, we are stuck, right? We cannot really solve even for the single derivative of c, leave apart the third derivative, which is what we want in actual. So let us see if we can do something with this m prime of xt. So we know for a fact that our cxt is equals to log of mxt. So this will hold true not only for s, but also for my x random variable. So let us try to derive for this and see what happens. So I'll take the first derivative of this guy. What will I get here? Anyone? So I'll be initially taking my derivative with respect to t of log of mxt, right? So what will I get here? So if I'm taking derivative of log of something, that itself will come right here in the denominator, and I'll have a mxt prime in the numerator. Does everyone agree with this?
Yes, ma'am.
Right? Okay. So now again, we don't care about the general MGF. We do not care about the general CGF. What we care about is what happens to our CGFs and MGFs when we substitute in the value of 0. Because this is our end goal, right? And we need 0 at the end. So let us try to do that. So we evaluate this thing at t equals to 0, which will render this guy as expectation of x, right? Because that is what is our cx0. Cx prime 0 is expectation of x, right? So does this make sense to everyone?
Yes.
Yes, ma'am.
What about others? This is really important.
Yes, ma'am.
What about the rest of you guys? Take a minute or two to understand what I just did there. Does this make sense to everyone now? Any doubts? So again, remember our end goal is to figure out the skewness for our S guy, but we tried to do that, but got stuck with M prime of xt, right? So now we are trying to figure out the value for my mx prime of t. And I do know my expectation of x. I mean, not exactly, but I know that I can write it as m1, right? And I have this guy here, mx prime t and mxt. So we'll try to see what we can do here. But I want you all to, say a yes or a no if you have understood this or not.
Yes, ma'am.
Yes, ma'am.
I've had 2 yeses and we have 5 students. What about others? Do not hesitate to ask me if you haven't understood this. All right. Okay. So now, next step, what we can do is, maybe we can substitute this t as 0 within these guys. So what I'm going to write here is m prime of x instead of t, I'm just going to put 0 here upon mx of 0. And instead of expectation of x, I will just write m1, right? Because that is how I define my expectation of x in general. So if I'm talking about mx0, what is my mx0? What will it be? It will be expectation of e raised to t times 0, right? Which is expectation of 1, which is just 1 itself. So this denominator can just, go away. I have nothing to do with it. So what I will be left with is m1 equal to m prime of x0, right? So I know that my expectation of x, which is my m1, is just m prime of x at t0, right? Okay, so this will be useful to us later on. We'll have a look. But again, let us try to be mindful. And what we can also do is, let us also try to have a look at c double prime. So if I want to have a look at c double prime of xt, what will I get? So I'll have to differentiate m prime of xt upon m of xt here. Again, with respect to t. So what do you guys think I will get here?
It will be mxt into m double dash xt minus mx double mx dash t the whole square.
Minus
mx dash t the whole square.
Right.
The whole upon mxt the whole square.
Right. Everything will be divided by mxt the whole square. So here I can just forget this one mxt and I can write one mxt here, right? And here I can instead write mxt here and just extend these brackets. Does this make sense to everyone? So basically I have just used u upon v formula. Nothing complicated. Okay. All right, and you get this as your answer. So again, can I do something else? So if you try to compare this, now again we equate, okay, let me just, take this at 0. So it will become what? My variance for x, which will be equal to m double prime of x evaluated at 0, and mx0 will again be 1, right? And this will be minus mx prime of 0, and that will again be just 1, and this I have as square here. So if you have a look, if you compare, how can I rewrite this as? I mean, it's in a way something like this, which is my general definition of variance of x, right? All right, so we'll see if we can use this somewhere to derive this skewness. So again, now let us try to see how can we derive this skewness. So maybe, so we were stuck here, right? So what can we do next? So if I were to derive, if I were to differentiate this again, what will I have? I'll have C prime S T. So double T, and this will be equal to d by dt of this guy, right? So lambda m prime of x of t. So what do you guys think will happen here? I'll have lambda d by dt m prime of xt, right? Which is nothing but lambda times m double prime of xt, right? Does this make some sense?
Yes, ma'am.
So now can you guys guess what will happen with this C triple prime of S of t? It will be d by dt of lambda times m double prime of xt, right? Which will just be lambda times m triple prime of x of t. And I can just rewrite this as m3, right? So this can just be lambda m3. But again, you know, what I'm doing here is I should ideally have P as 0 everywhere, right? Because if I'm looking at my skewness here, right? So this is when essentially my C double prime of S of t evaluated when t is 0 to give me the skewness of S. All right. So now is this sufficient enough to see whether my S is positively skewed, negatively skewed, or symmetrical? Do we look at the value of skewness or do we look at something else to determine the skewness? Anyone? Do you guys remember coefficient of skewness?
We look at the sign.
Yeah, so we look at the sign of
Coefficient of skewness.
exactly right. So we look at the sign of coefficient of skewness, and what is the formula? It has skewness of S in the numerator, and in the denominator it will have variance of S raised to 3 by 2, right? Okay, so we derived the skewness as lambda times m3, and we had our variance as well, right? Which was just lambda times m2. So did you guys notice what was my expectation for S? It was lambda times m1. What was my variance for S? Lambda times m2. What was my skewness for S? Lambda times m3. So this is a very nice property, and this is, I think, one of the reasons why I really like Poisson distribution, because it's just pretty nice and cool. All right, so this is just 3 by 2. Okay, so now we have to determine this, the sign of this guy here. What do you guys think? Will it be positive? Will it be negative? Can it be 0? Anyone? So it depends on the sign of lambda. It depends on the sign of m3. It depends on the sign of m2. What do you guys think? How will it determine the sign of the coefficient of skewness that we have? Are you guys there? Hello, do I have you all?
Yes, ma'am.
Yes,
All right. All right. So are you guys thinking?
lambda will be positive
Lambda will be positive, right? Because that is the parameter, the rate at
parameter.
which, yeah, exactly. So it has to be positive. Okay. What about others?
Ma'am, even M2 will be positive, like it's a variance and that is why.
Exactly. It's a variance. Is okay. No. Is M2 variance? M2 is not variance. M2 minus M1 square is variance, right?
Oh, all
M2
right.
is just expectation of x squared.
If M2 is expectation of x square, it has to be positive then, right?
Why?
Because it's a square, right?
Yeah, right. So what is M2? M2 is my expectation of x squared. So remember, if I'm writing my expectation of x squared, what is it? It is just the probability times x square. So whatever value my x takes, uska square aa jayega, times the probability that it will happen. So probability will always be positive, and yes, square it, this will also be positive. An addition of all the positive terms will give you something positive. Very good, Vaibhav. So we have M2 as positive. Now what about M3?
Ma'am, then by the same logic, M3 will be negative
M3 will be negative. Why?
because then it will be raised to 3. Maybe it will
Yeah.
be expectation of x cubed, so it will be raised to 3.
So
All right, no, I mean it will be positive for positive numbers. Still.
did you? Yeah, exactly right. It can be positive for positive numbers and negative for negative numbers. So
Yeah.
what do you guys think is the value of x? What does x here represent? Can it be negative anytime? What is my x here?
No, same amount, so it won't be negative.
It won't be negative. Exactly. Right. So even my M3 will be positive. So if everything is positive, then I know that, this will be positive. So I can say that my S is a positively skewed distribution. But again, what happens if my lambda goes to infinity? So let us say if lambda goes to infinity, then I know that my lambda m2 raised to 3 by 2. Okay. So I have infinity in the numerator and I will have infinity in the denominator as well. So what do you guys think will happen? I have lambda m3 here and I will have lambda raised to 1.5 m2 here. So I can rewrite this as m3 upon lambda raised to 0.5 m2, right? So I have infinity in the denominator. I mean, it is tending to infinity. And therefore, with a positive exponent to lambda in the denominator, if lambda goes to infinity, lambda raised to 0.5 will also go to infinity and my coefficient of skewness will tend to 0, which will render S to be symmetric, right? Does this make some sense? Yeah. Any doubts in regards to what all I have done? So what I just did was, I wanted to see what happens. So I know that my lambda is positive, right? But if my lambda tends to infinity, which in general is not going to happen, but just in theoretical sense, if I say that my lambda is tending to infinity, then I can have maybe, my coefficient of skewness either infinity or 0, depending on whether my lambda stays in the numerator or in the denominator with a positive exponent. So what I have here is, I have lambda upon lambda raised to 1.5 because 3 by 2 is just 1.5 and I have taken this outside. Oops, m2 should be raised to 3 by 2 here. Again 3 by 2 here. Okay, so we have m3 upon lambda raised to 0.5 because lambda raised to 1 was in the numerator and I took this here and 1.5 minus 1 gave me 0.5. And 0.5 is a positive number, right? So I'll have infinity raised to 0.5. So it will tend to infinity in a sense, as in when my lambda goes to infinity. And I know that my 1 upon infinity will tend to 0, which is why my coefficient of skewness will tend to 0. And I know that if my coefficient of skewness tends to 0, then my S will be symmetric. When lambda goes to infinity only. All right. Can't really select that. Any doubts with what I have written here?
No, ma'am.
Thank you, Anvya. What about others?
Clear, ma'am.
No, ma'am, no doubts.
Thank you. And what about the rest of you guys?
No, ma'am.
All right. So let us try to, okay, so we can do the same thing with binomial distribution and negative binomial distribution, which we will do. But even before that, I want to introduce you guys to another thing. So what we had a look at right now was S, right, which was sum of individual policies, which were X's. So X1 is one policy, X2 is another policy, X3 is another policy, let's say, right? And then we added all of them to make one particular portfolio of policies, which was S. So now if I, as an insurance company, care not only about one particular portfolio, but about all the portfolios in general. So now what I'm going to do is, so remember we added all of these X's to get one S. So now I'll be adding all the other S's to get one something which is A. So basically what I will be doing is a sum of compound Poisson distribution. So remember, this S is one compound Poisson distribution. And what I will be doing now is a sum of those S's. And that is why I call it sum of compound Poissons. All right. So, okay. Again, the definition would be kind of similar. So I have S1, I look at S2, and so on up until, let's say, Sn, right? And remember, the assumption that I'm making is that these are independent random variables. Okay. And let's say now this S1, S2, Sn is each of these S's that we defined here, right? So my S here, so if my N here follows Poisson with the parameter lambda, my S, which is a compound Poisson distribution, also follows Poisson distribution, right? So now what I'm going to do is, instead of writing as lambda, because I have different S's, I will have subscripts to all of my parameters. So in a way, I'm saying that my Sn will follow Poisson distribution, compound Poisson distribution with the parameter lambda n. So for this guy, I'll have lambda 1. For this guy, I'll have lambda 2. And so for this guy, I'll have lambda n. And now I'm looking at the sum of all of these. So S1 plus S2 up until Sn. And I denote this by A. So this A here is the sum that is of interest to me. So this is the sum of compound Poisson distributions, right? So now I have to figure out what happens to A. What distribution will it follow? Will it follow Poisson distribution again? We don't know. So, okay, the derivation for this thing is really not in the syllabus, and I think it's really not that difficult either, I would say. So, but again, you know, just to start off with what we will be ending up with, let me just say that, you know, A here will also follow Poisson distribution, but with some parameter, which is this. So does anyone know what is this? So this is also known as lambda, but this is the capital lambda. So just a way to denote a capital lambda. So how will I define it here? So my capital lambda here is actually summation of all of these lambda i's, where I goes from 1 to n. So do you guys remember the sum that we started off this lecture with? We had two Poisson distributions, n and m, and we added them together, and we got another Poisson distribution, which was v, right? And the parameter it followed Poisson with was small n, sorry, lambda plus mu, right? Which were the initial parameters that we started off with for n and m respectively. So here, it's kind of the same thing that's happening, right? So this guy has lambda 1, this guy has lambda 2, this guy has lambda n. And I'm adding up all of them together to give something which is A, which I say is, you know, the aggregate aggregate of the aggregate claims, right? And now if I have to figure out what will be, so I'm just generalizing it and saying that this is how I denote my capital lambda, which is just instead of summing up 2, we are summing up n here. So instead of having lambda 1 plus lambda 2, I have lambda 1 plus lambda 2 up until lambda n. So I summarize it like this, and that is how I denote my capital lambda, which is the rate at which this A follows poisson. So again, what happens is, again, because it's a Poisson distribution, I can fairly say that this will be my expectation of A as well. Because this is the rate at which events are occurring. So this is my expected A here. All right. But again, expectation is not really something that we only look for. We also need to know the f of x's and everything else. So just some housekeeping work. So when I say f of x here, it denotes something about A. And if I say f of I x here, it will be something about Si. So not exactly. So yeah, it will be something about Si. So let's say if I'm saying, f1x, that is the distribution of S1. I mean, it's, yeah. And your S2 follows f2x. But your A follows fx. Okay. So now if I were to write my definition for f of x, so this again we aren't going to necessarily derive, but is very intuitive. So what do you guys think should be okay, let me maybe write it and then I will not explain it, and I want you all to see and infer from this what does it mean intuitively. So I have lambda I here and I have fi of x here. Yeah. So this is how I define my f of x. And now I want any one of you or as many of you to explain me this intuitively, even before I explain it to you guys. So what is really happening there? Can anyone guess? Can you guys see what's going on there? So what is lambda I? Anyone? What is my lambda I here? Hello. Am I audible?
Yes, ma'am.
Right. So what is lambda I? Are you guys awake?
Parameter of the ith compound, this poison.
So it is the parameter of my SIs, right? Which themselves follow compound Poisson distribution, right? What is my capital F of IX? Mihir, what is my
S1,
capital
S2,
F?
S3.
It is the distribution, the CDF, right? It is not S1, S2,
Yes.
S3, it is the CDF
S
of S1, S2, S3, right? And Webber, what is my capital lambda?
I'm sorry, were you asking me?
Yeah. What is my capital lambda?
Capital lambda is just the summation of all lambdas, right?
All lambda i's, right? Yeah. So what did you guys think about what I have written on the board? So if you forget about, if this is f of x or whatever this is, what I have is summation of the parameter lambda i's times fix, right? Times the thing that we're going to observe, the chance of it being observed, and I'm dividing each of these things with capital lambda. And what is my capital lambda? Web have just said, right? It is summation of all the lambda i's. So in a way, I am taking weighted average of the distribution functions. So my weights here are the lambda i's, and my quantity of interest is the capital Fi of x, and I'm assigning the weight of lambda i's to each of those Fi's and then dividing it by the sum of all those weights, right? Which is my capital lambda. Does this make some sense?
Yes, ma'am.
To everyone? So this is in a way just the weighted average of my distribution function. All right. So, I mean, we can actually, derive the fact that RA actually follows compound Poisson distribution using the MGF. So for that, we will have to use, first of all, the fact that my capital F can be written in such a manner, and then we will verify that if I use this, do I get this? And if I do, then I know that this is in sync and I was correct from the start. So let us try to do that. And what I will be doing right now is just writing the MGF for my A guy here. Okay. So I will write MGF for my A, and I'll be denoting as MA of T, which is nothing but expectation of e raised to T times A, right? So I can again rewrite this as expectation of e raised to T times S1 plus S2 till Sn, right? And again, I know that these are independent of each other. So I have pi, I going from 1 to n, expectation of e raised to T times Si's. Is this clear to everyone up until here?
Yes, ma'am.
Yes, ma'am.
Right? So, okay, now if I have a look at this thing right here, what does this look like? Does it look something like M of SIT? Right? It does look like the MGF, right? Of my guy SI here. So, do you guys remember if my SIs follow compound Poisson distribution, what was the MGF? So I'm talking about this, right? So we know that each of my S guys follow compound Poisson distribution, and the MGF is e raised to lambda times mxt minus 1. So that is the same thing I'm going to write here, because this is exactly what I have, right? I have e raised to expectation of e raised to t times si. So the only difference is that we have denomination si here, because we're looking at various s's. So we'll have e raised to instead of lambda. Now I'm going to write lambda I, which will be corresponding to this particular si. And instead of mxt, now I have to write mi of t, right? Minus 1. Does this make sense to everyone? Can I simplify it further? How will I simplify this further? Anyone? So if I have summation of all these EIs, so let's say, sorry, multiplication. So let's say if I have e raised to a, e raised to b, e raised to c, I know I can write this as e raised to a plus b plus c, right? And which is what I have here as well, multiplication of all of these terms. So what I will do is I will write e here, and in the exponent, I'm going to sum it up across n, and this will be as it is. All right. So the next thing that I'm going to do is, now I have to do a bit of hera-fairy, I would say. So what I'm going to do is, first of all, I'll just expand this. So I will get summation of lambda I, MIT, I going from 1 to n, minus summation of lambda I going from 1 to n, right? Because this lambda I, and we have a bracket here, so this lambda I will get multiplied and this summation will go across as it is. So again, I can rewrite this guy here as my capital lambda I. Here I cannot write because I have MIT multiplied to my lambda I. So this will remain as it is, minus capital lambda, and here I goes from 1 to n. So now what I will do is, I will take this lambda outside as the common. So I know that I do not have the capital lambda here. So what I will do is, I will multiply and divide by lambda. So I have already multiplied by lambda and taken it outside as the common. And what I will be left with is this thing upon capital lambda minus 1, right? Does this make some sense?
Yes, miss.
Yes. So now if I have to compare this MGF with the MGF of anything that we have, I mean, it's already, the secret is already revealed to you guys, right? That our A follows Poisson distribution. So just have a look at your table booklets and see what parameter and how does the MGF of the Poisson looks similar to this A guy here. Does it look any similar? Do I have you all? Does it look similar to the MGF of Poisson distribution?
And what about the e raised to 2 that is inside?
What is? Please pick up a bit louder.
The e raised to t part.
Yeah, right. It doesn't look quite similar to us, right? But again, so first question, should it look similar to Poisson distribution or should it look similar to compound Poisson distribution? So remember the question that we did initially was adding up two Poisson distributions. So we got one Poisson distribution. But here, did we add simple Poisson distributions? No, right? We added compound Poisson distributions. So the MGF that we would have should be comparable to another compound Poisson distribution, right? So if we go back, I mean, even if we don't go back, we can have a look here itself because we did use that, right? So this is how the MGF of a compound Poisson distribution looks like, right? We have e raised to the parameter for SI. So here we have e raised to the parameter for A. Okay, cool. -1, But what about this? We have MIT here. So what is MIT here? This MIT, let me erase this. So this MIT that I have here is my MGF of S, right? So here I should want, so I want this to be the MGF of, what do you guys think? Oh, what was my MIT here? Was it the MGF of S? No, right? What was this MGF of? Can anyone remind me? This wasn't the MGF of S. What was this the MGF of?
X.
X, right? So this was the MGF of the stuff that I added up together to give S, जिसके लिए हमने ये निकाला था MGF. So here I'm adding up S's. So now I want this thing to be the MGF of S, right? Are you guys there? Do you guys agree with what I have said up until now?
Yes, ma'am.
Okay, so remember, so now what I'm going to do is, I'm going to derive my M of T here, which will be, let me just do it maybe, okay, I think I should just do it here. All right, so I'm going to derive something which is M of T here. So if I have to derive my M of T, what do I have to do here? So remember, what is my F of X? My F of X is this. So if I were to write using this, my small f of X, what will I get? The differentiation of this. So it would just simply be summation I going from 1 to n lambda i's, because this all is just a constant. And if you differentiate this, you will get fi of X. So this is what I'm going to use now. And what I will write here is, for this guy, I know that I will get integration from 0 to infinity e raised to t x 1 upon capital lambda summation lambda I fi of X. where I goes from 1 to n, right? And I should not forget dx, right? So this here, remember, is if you differentiate this guy, all right? So now, again, what I'm doing is I'm just going to take some constants outside. But remember, I cannot take anything which depends on x here outside. So I cannot really take this outside. But again, this summation has to be applied. So what I'm just going to do is I'm going to take this summation outside so that it still stays for all the i's. And I'll just have this integration here, which will be e raised to tx times fi of x dx. And now if I see, this will be 1 upon lambda summation of lambda i's, where I goes from 1 to n. And how can I rewrite this thing as now? Can anyone see? What is this? This is e raised to tx fi of x dx. How do you guys say I rewrite this here? So it looks a bit like expectation of e raised to tx, right? This is the PDF of something, and this is e raised to tx multiplied to the PDF, and then we are taking integration from 0 till infinity, right? Which encompasses all the values that our x can take. So this essentially will be the MGF. So I can rewrite this as MI T here. So I can again maybe shade it. Is this part clear to everyone?
Yes, ma'am.
Yeah. So now if you have a look at what we have here and what we just derived here, does it look similar?
Yes, ma'am.
It does, right? So what I can rewrite this as my capital lambda here, and then m of t here minus 1, right? So now if I have a look, this indeed looks like a compound Poisson's MGF, right? So any doubts with what we have done up until now? So this is all that we are going to cover today.
No, ma'am. Thank you.
All right. What about others? Okay, so again, I think today's session was a bit technically heavy. I do understand that. So again, I think you guys do have a bit of a time to go through all of these derivations and do understand them in detail. And I think I'm sure you guys will have or might have some doubts when you go through this again at your home. And please do not hesitate to message me. I will not be in the town, but again, I can still answer your queries and questions. So yeah, as and when I'll be free.